All right, today we're going to talk about the invisible glue that holds the entire universe together, chemical bonds. We're going to break down the basic rules for how atoms link up to build, well, everything, from the salt in your shaker to the water in your glass. Let's dive in. I mean, have you ever really stopped to think about that? It's a huge question, right? And the answer is all happening at the atomic level. At its core, chemistry is just the story of atoms looking for one thing: stability. And how they find it? Well, that's what explains pretty much everything we see.
So let's start right there with this idea of a quest for stability. You can kind of think of atoms like people. They're all just trying to get to a comfortable, low-energy place. But for an atom, what does stable even look like?
Well, to figure that out, we've got to look at the cool kids of the periodic table, the noble gases. We're talking helium, neon, argon. These guys are the atomic elite. Why? Because their outer electron shells are completely full. This makes them super stable and, honestly, kind of boring. They don't react with anything. They don't need to. They've already won the game. And every other atom is just trying to be like them. Now, this whole drive has a name, and it's a super important one: the octet rule. Octet just means 8, and the rule is simple. Atoms are happiest, they're most stable, when they have 8 electrons in their outermost shell. This is the playbook for all of chemistry. It's what forces atoms to either gain, lose, or share their electrons just to hit that magic number 8. So how do they get it done? Well, they've basically got 2 main strategies. The first move is a simple transfer. One atom gives an electron away, another one grabs it. The second move is more of a partnership. Atoms decide to cooperate and share electrons. These 2 different paths lead to the 2 main types of chemical bonds we're about to get into. Okay, let's tackle that first path, the transfer. This is what leads to an ionic bond, and it's really a simple story of a giver and a taker. And the perfect example is plain old table salt, sodium chloride. So you've got sodium over here, a metal with 1 extra electron that it is desperate to get rid of. And then you have chlorine, a nonmetal that's just 1 electron away from having a perfect set. It's a match made in heaven. Sodium happily gives away its electron to chlorine. Now, sodium has a positive charge, and chlorine has a -1. They've become what we call ions. And this is the part you really gotta get. The bond isn't the electron jumping over. Nope. It's what happens after. That positively charged sodium and that negatively charged chlorine are now powerfully attracted to each other. You know, opposites attract. That magnetic-like force between them, that's the ionic bond. But what if nobody wants to give up their electrons? What happens when you have 2 atoms that both want to gain an electron? Well, that brings us to our second strategy, the partnership. This is what forms a covalent bond. And our star player here is water, H2O. Oxygen needs 2 more electrons to be stable, and each of the 2 hydrogens needs 1. But nobody here is just going to give their electrons away. So they work out a deal. They decide to share. Oxygen shares an electron with each hydrogen, and each hydrogen shares its electron back with the oxygen. By forming these shared pairs, everybody gets to feel like their outer shell is full. It's a total win-win. And that, in a nutshell, is a covalent bond. It's not a giveaway, it's a team-up. It's a cooperative agreement where atoms work together to get stable. A true partnership. Okay, so we've got our 2 main strategies, the ionic transfer and the covalent partnership. But, what's the big deal? How do these tiny little decisions between atoms actually affect the world we see and touch every day? Let's put it to the test. This is the real question, isn't it? Why should we care if salt is ionic and sugar is covalent? Well, it turns out that the type of bond a substance has determines basically everything about it, and we can prove it with a really simple experiment. So, let's grab 2 things from the kitchen, salt and sugar. We know salt is ionic, and sugar is a classic covalent molecule. Now, what do you think is going to happen if we dissolve both of them in water and then try to pass an electric current through the solutions? And the results are in. The salt water, yep, it conducts electricity like a champ. But the sugar water, nothing. It's an insulator. So there it is, a direct link. The type of bond completely changes a substance's properties. So why the huge difference? Well, it all comes down to what happens when they dissolve. When that ionic salt hits the water, it breaks apart into all those positive and negative ions, and those charged particles are now free to zip around and carry an electric current. But the covalent sugar, Its molecules are held together so strongly that they just float around as whole neutral chunks. There are no free charges, so there's nothing to carry the current. Simple as that. This simple little test shows us a really profound truth. The choices that atoms make on an invisible, microscopic level have massive consequences that we can see and measure. For a substance, its bond type is its destiny. And that is the big takeaway here. These invisible connections between atoms are what define the visible properties of absolutely everything. Whether something is hard or soft, whether it's a solid or a gas, whether it conducts electricity, it all comes back to how its atoms are bonded together. So I'll leave you with this final thought. We just saw how bonding determines if something can conduct electricity. But what else? What about the insane hardness of a diamond, or the boiling point of water, or even the color of a gemstone? Yep, all of those things are also written in the language of chemical bonds. This invisible quest for stability is literally the architect of the physical world we experience every single day.